Hey fellow nerds, today we will solve all the gate problems on diode circuits from 2015 to 2024. This is our first problem. As shown in the circuit, the initial voltage across the capacitor is 10 volt with the switch being open. Now the switch is closed at t equal to 0. What we want to find out is the total energy that is dissipated in the ideal Zener diode whose Zener voltage is 5 volt once the switch is closed. It has to be found in millijoules rounded off to 3 decimal places. Let's figure it out. We have a Zener diode in the circuit. Its Zener voltage is 5 volt. So it will be switched on as long as it gets a 5 volt potential across it, positive on the N side, negative on the P side. Because a Zener diode works in the negative bias region. At t equal to 0, when the switch is just closed, the capacitor will have a potential 10 volt across it. The Zener diode will be on and we can model it as a cell with potential 5 volt. The rest of the 5 volt will be dropped across the resistor. So at t equal to 0, we can model the circuit like this. Now, what we have over here is basically a RC circuit. Capacitor is charged and it has a potential 10 volt across it. Now, since the switch is closed, the capacitor is going to discharge. When the capacitor discharges, potential across it will exponentially decrease. As a function of time, we can write potential across the capacitor is its maximum value e to the power minus t by tau, tau being the time constant. It is the product of R and C. Let us find the value of time constant first. Time constant is RC. R is 10 kilo, C is 10 micro. So we get time constant is 0.1 second. Let us write an expression for the potential drop across the capacitor as a function of time. Like we said, it is the maximum value multiplied by e to the power minus t by RC. Maximum value is 10 volt. RC is 0.1. So we get 10 e to the power minus t by 0.1. 1 by 0.1 is 10. So let us write 10 e to the power minus 10t. Now, I also want to find an expression for the current in the circuit as a function of time. Since the capacitor is discharging, initially the current is going to be really high and then it will exponentially decrease. So current as a function of time will be its maximum value, which is the initial value, multiplied by e to the power minus t by tau. Current is maximum at t equal to 0. At t equal to 0, the resistor has a potential 5 volt across it. Value of resistance is 10 kilo ohm. So the current that is flowing through it is 5 divided by 10k or 0.5 milliampere. So if we write an expression for the current as a function of time, it is maximum current e to the power minus t by RC. Maximum current is 0.5 milliampere. 1 by RC is 10. So we get the current, it is 0.5 e to the power minus 10t milliampere. Now comes the most important part of this question. We saw that at t equal to 0, when the switch is just closed, the diode is on, so it has a potential 5 volt across it. Capacitor has 10 volt, so the rest of the potential, that is 5 volt, will be dropped across the resistor. Now the potential across the capacitor will decrease exponentially. But as long as the diode is on, potential across it will be constantly at 5 volt. That means when the capacitor discharges and the potential across it decreases exponentially, the potential across the resistor also decreases. Diode will constantly be at 5 volt. Now, the resistor has 5 volt initially. It will decrease. At some point, the potential across it will become 0 volt. The Zener diode will still have 5 volt. That means the capacitor will have 0 plus 5 volt across it. But the voltage across the capacitor is still decreasing. Now, if it goes below 5 volt, that means the diode is not getting 5 volt across it anymore. That will make the diode switched off. So this is the idea. When the potential drop across the capacitor becomes less than 5, the diode will switch off. Or the Zener diode will be switched on only until the potential across the capacitor reaches 5 volt. After that, it will switch off and there will be no current in the circuit and there will be no energy dissipation. So when they said we have to find the total energy dissipated in the ideal Zener diode, we only have to consider from t equal to 0 to whatever time at which the capacitor voltage becomes 5 volt. That means the next thing we have to find out is the time at which the voltage across the capacitor becomes 5 volt. We already have an expression for the voltage across the capacitor. It is 10 e raised to minus 10t. We have to find out when this becomes equal to 5. So let us do that. We have 10 e to the power minus 10t is equal to 5. From this we can write e to the power plus 10t is 10 by 5, which is equal to 2. Taking natural logarithm on both sides, we get 10t is log of 2, or t is log of 2 divided by 10. Log of 2 is 0.693. So t is 0.0693 seconds. The diode will be on only for 0.0693 seconds. Throughout the time it is on, the potential across it is going to be constantly at 5 volt. Current through it is going to be 0.5 e to the power minus 10t milliamperes. What we have to find out is the total energy. We know energy is the product of voltage and current. Here voltage is a constant, it is 5 volt, but I depends on time. So we have to integrate it. Energy dissipated is the integral of Vz I of t dt. Vz is the potential across the Zener diode, I of t is the current that is flowing through it as a function of time. Now, what will be the limits of integration? Here the variable with respect to we are doing the integration is t, and time takes value from 0 up to 0.0693 seconds. Because after that the diode is off, no current is flowing in the circuit and there is no energy dissipation. Now current as a function of time is 0.5 e to the power minus 10t. Let us write it that way. We have 5 multiplied by 0.5, it is 2.5. 2.5 is a constant, so let us take it out of the integration. We have to integrate e raised to minus 10t. It is 1 by minus 10 e raised to minus 10t. And the limit is from 0 to 0.0693. So we can write it this way. Now 2.5 divided by minus 10 is minus 0.25. Also giving the upper limit, we get e to the power minus 0.693. Giving the lower limit, we get e to the power 0, which is 1. Now, if you calculate e to the power minus 0.693, it is approximately equal to 0.5. 0.5 minus 1 is minus 0.5. So the energy dissipated is approximately negative 0.25 multiplied by negative 0.5, which is 0.125. The current was in milliampere and Zener voltage was in volt. So this will be in millijoules. In the question, we have to find the total energy dissipated in millijoules rounded to 3 decimal places. So the final answer is 0.125. Let us see the next problem. In the circuit shown, the n:1 step-down transformer and the diodes are ideal. The diodes have no voltage drop in forward bias condition because they are ideal. Now, if the input voltage is 10 sine omega t and the average value of the load voltage is 2.5 divided by pi, we have to find out the value of n. This is a very simple question once you recognize the circuit. What we have over here is a center tapped half-wave rectifier. And the average value of the output of a center tapped half-wave rectifier is 2V0 divided by pi, V0 being the maximum value. In the question it is given that the average value is 2.5 divided by pi. So 2V0 by pi is actually 2.5 divided by pi. which means V0 has to be 1.25 volt. Let's look at the question again. Input is 10 sine omega t, which means its maximum value is 10. So we are giving 10 volt here, but we are getting 1.25 volt here. If the transformer steps down 10 volt to 1.25 volt, that means 10 by 1.25 should be equal to n by 1, or n is 4. Option A is the correct answer. Let's see the next problem. We have a circuit given. D1 and D2 are silicon diodes. They have a cut-in voltage of 0.7 volt. V in and V out are the input and output voltages in volts. What we have to find out is the transfer characteristics. We also have 4 options. Let's figure it out. The first thing we have to find out is what are the voltages at which D1 and D2 will be switched on and off. For that, this is what we are going to do. We will remove the diodes and figure out what is the potential drop we get across their terminals. If the potential drop is greater than 0.7 volt, we'll assume the diode is switched on. If it is less than that, we'll assume it is switched off. First, let us forget about D2 and check out D1. Now, assume D1 is off. That means no current is flowing in the circuit. We have a 1 volt supply over here. Since there is no current flowing through it, there will be no potential drop across the resistor. So we can assume at this terminal we get a 1 volt. So for D1 to be switched off, we at least need 1.7 volt on this side. That means D1 will be switched on as long as the input is greater than 1.7. It will be switched off until then. Let's write this down. Now let's forget about D1 and check out D2. D2 will also get 1 volt over here, but it is on its P side. So D2 will be on as long as the potential on its N side is less than 0.3 volt. Potential on its N side is the input voltage. So we can say D2 will be on as long as the input voltage is less than 0.3. Otherwise it will be off. Let us write that also down. Now, to plot the transfer characteristics, we have to check what the circuit does when V input is less than 0.3, when it is between 0.3 and 1.7, and when it is greater than 1.7. Let's take the first case. V input is less than 0.3 volt. V input is less than 0.3 volt. That means it is obviously less than 1.7. So D1 will be off and D2 will be on. Since D1 is off, we can model it as an open circuit. Since D2 is on, we can model it as a cell with potential 0.7 volt, like this. We have to find an expression for the output voltage. To make it more obvious, let me show V input over here like this. Now, V output can be shown between this point and the ground. Positive here, negative here. Now check out this loop. I'll start from the ground. I have V input from negative to positive. I have 0.7 also from negative to positive. Then I have V out from positive to negative. I go back to ground. So I can write plus V in plus 0.7 minus V out is equal to 0. Kirchhoff's voltage law. This gives me V out is V in plus 0.7. It might seem like I over-explained a little bit over here, but I have seen people struggling with KVL a lot. That's why I did it, and this will be the last time I'm doing it because now you get the drill. Let's take the second case. V input is between 0.3 and 1.7. Here V input is less than 1.7, and when V input is less than 1.7, D1 is off. V input is greater than 0.3. When V input is greater than 0.3, D2 is off. That means in this case, both diodes are off. Both diodes can be modeled as open circuits and the circuit will look like this. Now, V out is VR plus 1 volt. But since the circuit is open over here, there is no current flowing through the resistor R, and therefore there is no potential drop across it. VR is 0. So Vout is just 1 volt. Let's take the third case where V input is greater than 1.7. V input is greater than 1.7 volt, so D1 is on. V input is greater than 1.7 volt, so obviously it is greater than 0.3 volt, so D2 is off. We can model D1 as a cell whose potential is 0.7 volt and D2 as an open circuit. The circuit model will look like this. Now Vin is from negative to positive, 0.7 volt is from positive to negative, Vout from positive to negative. So I can write Vin minus 0.7 minus Vout is 0, or Vout is Vin minus 0.7. These are all the three cases we needed. Using what we found, let us plot the transfer characteristics. So I'll take a graph with Vin on the x-axis and Vout on the y-axis. Let us mark 0.3 and 1.7 on the x-axis. Now, when voltage is between 0.3 and 1.7, output is just 1 volt. So we get a horizontal line like this. When input is less than 0.3, output is input plus 0.7. This is of the form y is equal to mx plus c. M is the coefficient of V input, it will be the slope. Here it is 1. So we will have a straight line whose slope is 1. Its y-intercept is 0.7. So it will look like this. Slope is 1 and this point would be 0.7. When V input is greater than 1.7, output is input minus 0.7. This is also of the form y equals mx plus c. Coefficient of the input is 1. So here also slope of the graph will be 1. Y-intercept is negative 0.7. So it will look like this. Slope is 1. If you extend the line, you can see the intercept on the y-axis is at negative 0.7. So option A is the correct answer. Let us see the next problem. Here we have a circuit. The characteristics of the diode is given over here in this graph. The graph simply tells us that the diode switches on when the voltage across it is at least 0.7 volt. So the cut-in voltage of the diode is 0.7 volt. What we have to find out is the ratio of the minimum to the maximum small signal voltage gain rounded off to 2 decimal places. So in the circuit, we have a diode over here that will be switched on if it has a potential of at least 0.7 volt across it, and it will be switched off if it doesn't have that. So we only have two cases. Diode is switched on or the diode is switched off. If the diode is switched off, we will not have this entire branch. That means the output will be entirely taken across these two resistors. Now, if the diode is switched on, Vout will be taken across the diode and the resistor over here. So out of the two cases, we will have more output when the diode is not there and less output when the diode is there. So the gain will be maximum if the diode is switched off and it will be minimum if the diode is switched on. That's all we have to do here. Let's start with the case where the diode is switched off and the gain is maximum. The diode can be modeled as an open circuit and the circuit model will look like this. This is a very simple circuit. Input is divided between 3 equal resistors and output is taken across 2 of them. Or we can say input is divided between 6 kilo ohm resistance and the output is taken across 4 kilo ohm. So Vout is V input divided by 6 multiplied by 4, or V output is 2 by 3 V input. Now what we have to find out is the small signal voltage gain. It is the ratio of the small change in the output voltage to the small change in the input voltage. dVout by dVin. we got V output is 2 by 3 V in. It is like Y is equal to 2 by 3 X. Then if I want dy by dx, it is d by dx of 2 by 3x, which is 2 by 3. So here the small signal voltage gain is 2 by 3 and that is our maximum gain. Let's take the second case where D is on and the gain is minimum. Since the diode is on, we can model it as a cell whose potential is 0.7. Then the circuit will look like this. Now assume that a current I flows over here. At this junction, it will split into two. This part of the current will flow like this. This one will flow like this. Finally, at this junction, they combine again. So the current flowing through the 2 kilo ohm over here is again I. Current is flowing in this direction on the 2 kilo ohm. So we have positive potential here, negative potential here. For this resistor also, current is flowing like this. So it has a positive potential here, negative potential here. We will apply Kirchhoff's voltage law. I'll start from this point and go clockwise. V input is from negative to positive. Potential across the 2 kilo ohm will be 2 kilo multiplied by I. It is from positive to negative. As I go on, there is 0.7 again from positive to negative. As I further go on, there is potential drop across this 2 kilo ohm. That will also be 2 kilo multiplied by I from positive to negative. So I can write V input minus 2I minus 0.7 minus 2I is equal to 0. From this equation, I can write an expression for 2I. 2I is V in minus 0.7 divided by 2. Or I can write V in by 2 minus 0.35. Let it be there. Now, to find an expression for V out, I will take this loop. I'll start from this point and go clockwise. V out is from negative to positive. As I go on, 0.7 is from positive to negative. As I further go on, 2I on the 2 kilo ohm is also from positive to negative. So I can write V out minus 0.7 minus 2I is equal to 0. But we already found 2I in terms of V input. So let us put it over here. That gives us V out minus 0.7 minus V in by 2 plus 0.35 is equal to 0. That gives us V out is V in by 2 plus 0.35. Now what we want here is the small signal voltage gain, which means the small change in the output for a small change in the input. Basically dVout by dV input. So here we get V output is V input by 2 plus 0.35. For simplicity, I will write it as y equals x by 2 plus 0.35. Now, what I want is dy by dx. It is d by dx of x by 2 plus 0.35. d by dx of x by 2 is 1 by 2 plus d by dx of 0.35 is 0 because 0.35 is a constant. So here dVout by dV input, the small signal voltage gain is 1 by 2. And this will be our minimum gain. Now what we want is the ratio of the minimum gain to the maximum gain, that is 1 by 2 divided by 2 by 3, or we can write 1 by 2 multiplied by 3 by 2, which is 3 by 4 or 0.75. And that is our final answer. Let us see the next problem. If the circuit shown has to function as a clamping circuit, which one of the following conditions should be satisfied for a sinusoidal signal of period t? I'd say this is more like a theory question. What we have over here is a basic clamping circuit. Now, in the positive half cycle, we'll get positive potential here and negative potential here. So the diode will get a positive potential here, negative potential here. Assuming it is ideal, we can model it as a closed circuit like this. You can see that the input is directly connected across the capacitor. So when input increases from 0 to its maximum value, Capacitor will get completely charged and it will get a potential V0 across it, assuming V0 is the maximum value of the input. Now the input is at its maximum. It has to decrease from the maximum to 0. The question is, when that happens, will the capacitor discharge? See, the capacitor has positive potential on this plate and negative potential on this plate. So if the capacitor has to discharge, electrons from this plate have to go in this direction to the other plate. That means current has to flow in this direction. Can the current flow through the diode like this? No, because in that case, through the diode, current will be flowing from the N side to the P side, which is not possible. Let's consider the negative half cycle. Input decreases from 0 and it is negative the entire half cycle. The diode would get negative potential here and positive potential here. That means the diode will be reverse biased and we can model it as an open circuit. Now in this case, definitely the capacitor cannot discharge through the diode because it is an open circuit over here. But in both these cases, capacitor has one more path to discharge, that is through the resistor, like this. Or current can flow through the resistor in this direction. But we do not want that to happen. We do not want the capacitor to discharge. We want it to stay charged so that the potential across it stays a constant at V0. If the voltage across the capacitor stays V0, then V output that we get over here will be V input minus V0. And that is what we want as an output for a clamping circuit. So our requirement is the capacitor should not be able to discharge through the resistor. How do we make sure of that? By making sure that the time constant of this RC circuit is too large that half a cycle of the input is not enough for it to discharge. So time constant should be very much larger than the time period of the input signal. Time constant is RC, so RC should be very much larger than the time period of the input signal. The correct option is option D. Let's see the next problem. The output V0 of the diode circuit shown in the figure is connected to an averaging DC voltmeter. We want to find the reading on the DC voltmeter in volts, neglecting the voltage drop across the diode. This is also the simplest question once you recognize the circuit. What we have over here is simply a half-wave rectifier. So basically what we have to find out is the average value of the output of a half-wave rectifier, which we know is V0 by pi. V0 is the maximum value of the output, but this is a half-wave rectifier. Its output is basically the input itself with the negative half cycle removed. So its maximum value is going to be the maximum value of the input, which according to the question is 10. So the average value of the output is 10 by pi, which is 3.18 volt. And that is our final answer. Let's see the next problem. Assume that the diode in the figure has a cut-in voltage 0.7 volt, but otherwise it is ideal. What we have to find out is the magnitude of the current I2 in milliamperes. I2 is the current that flows through the resistance R2. Now, the first thing we have to do is check if the diode is on or off. For that, we'll do the same trick again. Assume the diode is off and remove it. Then find whatever is the potential we get across the two terminals. If it is sufficient enough to switch on the diode, then we can assume the diode is on. If it is not enough, then the diode is off. It's that simple. So let us check if the diode is on or off. Assuming the diode is off, I have removed it from here. Now we have a 2 volt supply across a 2 kilo ohm and a 6 kilo ohm. Now, whatever is the potential drop we get across the 2 kilo ohm is what we get across the diode. Potential across the 2 kilo ohm will be 2 divided by 2 plus 6 multiplied by 2, or 0.5 volt. So across these two terminals, we have 0.5 volt. This is less than the cut-in voltage of our diode. We at least need 0.7 volt. Now this means the diode will be switched off. If diode is switched off, the same current passes through R1 and R2. So according to Ohm's law, the current I2 is 2 volt divided by the equivalent resistance 2 plus 6, which is 2 by 8 or 0.25 milliampere. Why is it milliampere? Because the resistances are given in kilo ohm. So the final answer is 0.25. Let us see the next problem. Here we have two diodes D1 and D2. These are ideal and the capacitors are identical. The product RC is very large compared to the time period of the AC voltage. Assuming that the diodes do not break down in the reverse bias, we have to find the output voltage at the steady state. The input is 10 sine omega t. It is sinusoidal. In the positive half cycle, let us say it gives positive potential here and negative potential here. Then D1 will get positive potential here and negative here. It will be switched on. D2 also will get positive potential here and negative potential here. D2 will also be switched on. So in the positive half cycle, both diodes are on and we can model the circuit like this. Both diodes are modeled as closed circuits. Let's take a look at this capacitor. It is directly connected across the input. So when the input goes from 0 to its maximum value, which is 10 volt, the capacitor will get charged to its maximum value. Since negative terminal of the input goes here and positive terminal goes here, capacitor will have negative potential here, positive potential here. The same way for the second capacitor, negative terminal of the input is connected here, positive terminal is connected here. It will also get charged to its maximum with negative potential here and positive here. Since the maximum value of the input voltage is 10, at the maximum point, both capacitors will have 10 volt across it. Because basically the input is directly connected across both of them. Now the input is at the maximum, it has to decrease. Now the question is, when the input decreases from the maximum value to 0, will the capacitors be able to discharge? Well, actually no. Check this out. This capacitor has positive potential here and negative potential here. So for it to discharge, current has to flow in this direction. Can it discharge through the diode? No, because the diode looks like this. If current is flowing like this, that means current has to flow from the N side to the P side. That is not possible. Can it discharge through the resistor then? No, because in the question it is given, RC is very much large compared to the time period. The capacitor takes a long time to discharge through the resistor because its time constant is really large. It won't be able to discharge by the time the input voltage goes from the maximum to 0. Same thing happens with the other capacitor. It cannot discharge through the diode because that means current has to flow from the N side to the P side, which is not possible. It also cannot discharge through the resistor because RC is really large. So basically, when input decreases from maximum to 0, both capacitors will stay at 10 volt. Now, how about in the negative half cycle? In the negative half cycle, both diodes will get negative potential on the P side and positive potential on the N side. They will both be reverse biased and we can model them as open circuits. The circuit model will look like this. Again, the capacitors cannot discharge through the diodes. And since the time constant is really large, they cannot discharge through the resistor also. Basically, once they are completely charged, both of them will continue to have a potential 10 volt across them. With the first capacitor having positive potential here and negative here, and the second one having negative here and positive here. Now the output is taken across the two capacitors this whole time. So output is going to be plus 10 minus 10, which is 0. And that is our final answer. Let us see the next problem. In the circuit shown, assume that the diodes D1 and D2 are ideal. In the steady state condition, we have to find the average voltage VAB across the 0.5 microfarad capacitor. This is again the simplest problem once you recognize the circuit. This looks like a fancy circuit with a triangle shape and all, but we can draw it in a much simpler way like this. What we have over here is nothing but a voltage doubler circuit. Let me show you how it works. We'll start with the negative half cycle. In the negative half cycle, input gives negative potential here and positive here. So the diode D1 will get negative potential here and positive here. It will be switched on. Diode D2 will get negative here and positive here. It will be switched off. That means in the negative half cycle, D1 is on, D2 is off. So we can model the circuit like this. D1 is modeled as a closed circuit, D2 is modeled as an open circuit. Now the input is directly connected across the capacitor C1. We are talking about the negative half cycle. So when the input goes from 0 to the maximum negative value, capacitor will get charged to its maximum. Capacitor will have a potential V0 across it with negative here and positive here. The input is now at its maximum negative. Now when it becomes less negative or more positive, will the capacitor be able to discharge? If the capacitor has to discharge, then current has to flow in this direction through the diode. But take a look at the diode. If current has to flow in this direction, that means current has to flow from the N side to the P side of the diode, which is not possible. So in the second half of the negative half cycle, the capacitor will not be able to discharge. So the potential across C1 will remain V0. So basically what happens in the negative half cycle is that C1 gets charged to V0 with negative potential here and positive over here. Now let's go to the positive half cycle. Input will give positive here and negative here. That means D1 will get positive here and negative here, it will be switched off. D2 gets positive here and negative here, it will be switched on. We can model the circuit like this. We are talking about the positive half cycle, so assume that the input increases from 0 to its maximum value. When Vin is at its maximum value, we can model the circuit like this. Vin is at the maximum value, so over here we get V0. Let's apply Kirchhoff's voltage law. We have V0 from negative to positive. As we go on, again we have V0 from negative to positive. Further as we go on, we have the output VAB from positive to negative. So I can write V0 plus V0 minus VAB is 0. Or VAB, the output is 2 times V0. Right now, V input is at its maximum. Assume that it is decreasing from its maximum value back to 0 again. The question is, will the capacitors be able to discharge? No, because they don't have a path to discharge. So we can say when Vin further decreases from its maximum value, there is no path for both the capacitors to discharge. Which means at the steady state, the output will be constantly at 2V0. So basically, this is what a voltage doubler does. Its output will be constantly at 2 times the maximum value of the input. Over here in this question, peak value of the input is 50 volt. So at steady state, output VAB will be 2 times 50 or 100 volt. So the final answer is 100. Let us see the final problem. The diode in the circuit given below has a cut-in voltage 0.7 volt. It is ideal otherwise. What we have to find out is the current in milliampere in the 4 kilo ohm resistor. This is the 4 kilo ohm resistor. So the first thing we have to do here is to figure out if the diode is switched on or off. Depending on that, we have to draw the new circuit model and apply KVL KCL. So let's do that. I'm going to assume the diode is switched off. Then I'll figure out what is the potential drop I'm getting between these 2 points and check if it is enough to switch on the diode, for which I need 0.7 volt. I have marked the potential over here as V1 and the potential over here as V2. So all I have to check is if V1 minus V2 is greater than or equal to 0.7 volt. Since the circuit is open here, no current will flow through the 1 kilo ohm resistor, so we don't really have to care about it. All we have is a 2 kilo ohm, a 4 kilo ohm, a 3 kilo ohm and a 6 kilo ohm. We have a current source of 1 milliampere. Out of the 1 milliampere, some current will flow through the 2 kilo ohm and the 4 kilo ohm. I will call it I1. The rest of the current will flow through the 3 kilo ohm and then through the 6 kilo ohm. I'll call it I2. All I have to find out is V1 and V2. V1 will be the potential drop across the resistor 4 kilo ohm. V2 is the potential drop across the 6 kilo ohm. What about the 1 kilo ohm? We don't care about it because there is no current in it, so there is no potential drop across it. Let's do the math. V1 is the potential across the 4 kilo ohm. Current flowing through the 4 kilo ohm is I1, so potential across it is I1 multiplied by 4. Now what is I1? The 1 milliampere current has to split into 2 branches. One of the branches has 2 plus 4, 6 kilo ohm. The other one has 3 plus 6, 9 kilo ohm. So using current division, I1 will be 1 milliampere divided by the total resistance multiplied by resistance of the other branch. Multiplied by 4 will give us potential across the 4 kilo ohm. And this is 12 by 5 volt. Let's take a look at V2 now. V2 is the potential drop across the 6 kilo ohm. Current through the 6 kilo ohm is I2, so potential is I2 multiplied by 6. Now, to get I2, we have to apply voltage division again. It is 1 milliampere divided by the total resistance multiplied by the resistance of the other branch. This multiplied by 6 kilo ohm will give us V2. V2 is also 12 by 5 volt. So technically, at these 2 points, we are getting the same potential, which means the potential difference between these 2 points is 0. So if you put the diode D between these 2 points, it will not switch on because the diode needs at least 0.7 volt across it. So the diode is switched off. What we have to find out is the current flowing through the 4 kilo ohm resistor. Current flowing through the 4 ohm resistor is I1. So I4 is I1, which is 1 milliampere divided by 6 kilo ohm plus 9 kilo ohm multiplied by resistance of the other branch 9 kilo ohm. This is 0.6 milliampere, so our final answer is 0.6. Why is this milliampere? Because the current is 1 milliampere, the resistances in the denominator are in kilo. This is also in kilo. So kilo and kilo gets cancelled and finally the current is in milliampere. So that's all about it for today. See you in the next video. And please don't forget to subscribe.